logistics. So I think we'll just go ahead and get started now, and we'll hold the logistics announcements for the end of the session when everybody's here. So Jason MacDowell of GE, who is on secondment to ESIG for 2 years, is going to be chairing this session. It's another IBR session. If you thought yesterday's IBR session was intense, wait till you see this morning's IBR session. So got a great set of speakers, a great set of topics. So we're going to go ahead and get started, and I'm going to turn it over to Jason.
Good morning. Welcome back. How was the reception last night? Everyone have a good time? Great, great. I think a lot of us were trying to solve world problems last night, both during reception and maybe even more so after the reception. So it's great to see you back here all bright-eyed and ready to go. We're going to have a report out on that, solving the world problems here in the session today. So I think we've got a great session planned for you this morning. We have a panel of 5 experts that we're going to continue our journey around IBRs, and particularly focusing more not only on the technology itself, but what studies and modeling capability do we need to identify all of the attributes, the risks, and the mitigations as we go through this journey transitioning to a higher IBR grid. I don't want to take too much time. I just would like to introduce our 5 speakers just very high level now, and then we're going to go in detail one by one. Matt Richwine from Telos, Jin Tan from NREL, Ulrich Münz from Siemens, Yu Zhu from National Grid Electric System Operator, and Alex Shattuck from NERC. So with that, let's get started on our first panelist. Matt Richwine is a founding partner of Telos Energy and is a leader in power systems engineering, power electronic controls, and system stability. Over the past 13 years, he's been designing, testing, and analyzing thermal renewable power generation equipment and studying the stability of power systems ranging from tens of megawatts to tens of gigawatts. Please help me welcome Matt Richwine. Thank you.
Thank you, Jason. Can everyone hear me in the back? Okay, great. And thank you, ESIG. And thanks for a wonderful networking reception last night. I know that being the first panelist after the networking reception can be a little bit of a challenge, and especially when you're talking about voltage stability and some of those details. So that may be a cue for some of you to refill your cup of coffee. If you do, I certainly understand. But what I'm really excited to talk to you about is an effort we've been doing for a few years now, working with a few really great partners, MISO and the team, Nick Miller from Hickory Ledge, Rick O'Connell from Grid Lab and the team. And we're looking at what the AC stability concepts in support of long-range transmission planning. And so just to frame up what's motivating this effort, an emerging challenge, right? We have an expansive portfolio set looking at long-range transmission planning in the 10 to 20 year time frame with a high inverter future. There's a lot of ground to cover. There's a lot of scenarios to analyze and a lot of uncertainty in those future scenarios. Couple that with the practical challenges to modeling inverters, which is its own discussion that I won't get into here, but it's certainly there, and all with a quickly evolving technology. And so what do we do with that? Well, don't panic, okay? And contrary to popular belief, this is not a picture of me from my childhood, but it does illustrate some of the feelings around this. So before we figure out what to do with this, stepping back, the big picture of stability studies. And how I think about this and graph this is, you know, if you consider the level of detail of these studies on the x-axis and the burden of doing the studies on the y-axis, and by burden, I mean not just how many computers and how long does it take to run it, but the people to set up the models, to interpret and to make sense of the results, right? And so on the bottom left, you know, with a steady state analysis, you know, and really talking about a voltage stability type of analysis, like a PV analysis, you know, you have a relatively low level of detail and a low level of burden. And so you're able to do a lot of analysis there and consider a lot of different scenarios. But you're also not seeing the full picture of what those resources are doing. You jump up ahead to positive sequence, fundamental frequency dynamic simulations, tools like PSSC, TSAT, PSLF, et cetera, and you get a lot more detail about those resources, but it's also more demanding to set those up. The burden is significantly higher. And you end up with, at the extreme side is the electromagnetic transient simulation, tools like PSCAD, where you have the highest level of detail, right? It's the best that we can get. It's the closest we can get to the field, but it is also a significant burden on people and on computational capability. And what jumps out to me at this here is a gap, a need, an opportunity really to fill between some of the steady state analysis, the stuff that's tractable for large systems, lots of scenarios, while also capturing some of those details of what are these new resources doing for the system. A quick note on EMT, right? Why not just go and use the best tool we have, right? And so, in the words of Ice Cube, I think, EMT studies, it ain't easy, but it's necessary. Now, I'm not sure if Ice Cube was talking about electromagnetic transient simulations when he said this, but I think it applies, and it's sometimes, right? And when and where are important, right? And we really want to be strategic about how we're using these tools, especially those with the high burden, to make sure that we're using them on the scenarios and cases where we really need them. So now I'm going to take a step back about voltage stability and grid strength. And I don't have a lot of time to get into all the details, so I'm going to draw on some analogies that I like, that I think work really well. And actually, the trampoline analogy is one that was presented by Debbie 6 years ago at this conference, and I like it. I think it still works. And so, in short, to think about the challenge here that we're thinking is, if you consider a trampoline for as an analogy to the transmission system voltages, and the canvas of the trampoline being at some level value where the voltages are nominal, and they're supported by transmission lines or springs in this case, and ultimately supported by voltage anchors or the rail, which is conventionally those large synchronous machines. And as you load up the system, as you apply weight to the trampoline, you get deflection in the trampoline, just as you apply load to the transmission system, you have deviations in voltages. And so conventionally, with our weakening grid challenge, right, the retirement and decommitment of synchronous machines is akin to disconnecting some of those voltage anchors from the trampoline. And so that for the same loading that you have, or the same disturbance, you have larger deflections in your trampoline, you have larger deviations and faster deviations in your transmission system voltages, which manifests in control challenges for those resources. Now, in this example, in this analogy, right, the rail of the trampoline doesn't move, right? It's steel. It shouldn't be moving, depending on how hard your kids are jumping on them, I suppose. But that is like the idealized resource. And we know that there is no idealized resource that is perfectly controlling voltage. And so now I'd like to extend the analogy a little bit with the help of some characters, Spike and Chester. So if we talk about the resources not being idealized, not a rail, but as a couple dogs, and we've got our big dog, Spike, who is very good at holding that voltage reference locally. And so he's connected to the grid. And if you have a large resource that is good at controlling its voltage connected with a relatively short transmission line to the system, you end up with typically a strong grid, big resource, big transmission line. Similar setup, but with a smaller resource, right? Chester, not as able to control voltage locally where he is. And so if you jump on the trampoline, Chester's going to move a little bit more than Spike will. So you can have a weak grid there. And by extension here, if you have that large resource like Spike, who's very good at controlling voltage locally, yet you have a long transmission line to the rest of the grid, you can also have a weak system. And so in this way, we can start to differentiate between the resource types, their size, and how much effort they're putting into controlling their voltage. But it can go further than that. So extending this analogy, if you would allow me, a little bit more to the controls. And so what we see here in comparison is we have Spike, right, who's alert on the top, and he's holding that local voltage there and contributing to a strong grid is an immediate response to any deviations. right? And in contrast with, if Spike had a few too many at the networking reception last night, and he's maybe not as alert as he should be, in spite of his size and effort and ability to regulate that local voltage, he doesn't do it right away, right? And so this is the concept of the time, the response time, that is really important. And you need to not only be responsive in regulating voltage, but you need to do it in a time that matters, in the relevant timeframes. And so this is kind of framing up the argument that it's the quality of voltage regulation that really matters for voltage stability. And by quality, so how much effort are you putting into doing it? How quickly are you doing it? And you can't just crank up your control gains to get there. How well damped are you doing it? And so we're going to take this qualitative explanation here and start to put some numbers on it. There's a lot that went in, a lot of nuance behind developing this chart that I don't have time to get into, but I want to point out a couple key things. This on the y-axis is a grid strengthening metric. Higher being better. Higher is more like Spike, who's alert. Lower is more like Chester. Really what I'm plotting there is admittance in per unit. And that is really 1 over impedance. And if you think about those folks that are used to short circuit ratio screenings and grid strength, you recognize that 1 over impedance is akin to short circuit ratio. And so essentially, that's another way to look at it is if you have a higher short circuit strength, you're higher on this chart. And then I'm plotting this in the frequency domain. And so this was mentioned several times yesterday afternoon. Lucas, this is method 3. Deepak showed a few plots about showing this in the frequency domain. I'm zooming in on a particular band of the frequency domain that I think is most relevant. And in particular, it doesn't show up much here, but what's highlighted in yellow is kind of that 100 to 500 milliseconds after an initial event, which I would consider the really zooming in on a really critical time for voltage regulation and stable operation. And so then now to the traces. In red, the synchronous machine, this is kind of a reference for us. This is what we've known and used and done as an industry since its beginnings, right? And we see it has some level of grid strengthening. Okay, what does that mean? Well, now we can compare to some other technologies. And so in green, I'm showing the grid following inverter, an example of a real grid following inverter. So note, this chart was developed with real detailed PSCAD models in PSCAD to get to this view, right? So our grid following inverter, it does a big U, right? At the low frequency side on the left, it's high. It has some terminal voltage regulation, but it takes some time to work. So it shows up at the low frequency range, but then it tails off and it's pretty low actually in the band that I would consider fairly critical. So grid following inverters do not provide the grid strengthening effort that synchronous machines do according to this graph and according to basically all of our understanding, right? No surprise there. That can change. Grid following inverters are not a monolith, right? Similarly with grid forming inverters, which I'm showing in purple here at the top, there's a couple things to notice. One, grid forming inverters provide more grid strengthening than grid following inverters. Okay, expected. Also, they do it more than the synchronous machine example based on real synchronous machine parameters here. That's noteworthy. And 2, they do it for the whole range of interest here that I'm showing up to about 20 hertz here. So they are doing a good job regulating voltage for what I would consider to be really the critical bands for stability. So, okay, great. So we can quantify this. And one of the things I like about this plot is it's repeatable, it's standard, it's technology agnostic. You put any resource up there, grid following, grid forming, synchronous machine, you have a StatCom, any voltage regulating resource, you make up a new name for whatever that may be, grid forming, firming, I don't care what your marketing team decides to call it. You apply this process, this method, and you get this picture, and this is showing you what it's really doing. Admittedly, this is a small signal representation of it. This is not everything. I'll have to save that for another discussion. So great, we have this picture. We can compare resources easily. We can see what is doing what. What do we do with that? I'd like to introduce the concept of a dynamic impedance. And so with that, if you take the values in the critical band of admittance, take the reciprocal, turn them into an impedance, plug them into our very familiar Thevenin equivalent model with an ideal source behind what I'm calling a dynamic impedance, where that impedance is selected to represent those critical characteristics that were derived from those detailed models in terms of how good is that voltage controlled at the terminals of the resource for the periods that we want. And so for high grid strengthening resources like spike, that dynamic impedance will be low. Your terminals are electrically closer to your ideal source, as good as you could get. For poor grid strengthening resources like Chester or dozing spike, that impedance is larger. Your terminals are not as well controlled. They're farther electrically from your idealized voltage source. For any disturbance that happens, those terminal voltages are going to deviate more. And that is going to impact what the system is able, how much power transfer you're able to provide or to transfer across the system. So now I'm going to shift a little bit to a steady state analysis and looking at PV analysis for voltage stability. And just a quick refresher, on the x-axis here, we have power transfer, AC power transfer across the system, and on the y-axis, we have voltage. And we understand that as we load up the transmission system, as we transfer more power across it, voltage tends to decrease, and it ends up in a point where voltage collapses, where it's no longer able to support. And so these two curves are identical, and they are considering kind of what we would do today, in which those resources are, in which the terminal voltage is an ideal source. It's perfectly controlled in a steady state analysis, and you get a curve like that. And what we can see is if we now introduce a dynamic impedance to the resources, where that dynamic impedance is tuned and associated with a particular resource or category of resources, you can see it changes the PV curve substantially. And so for grid following, for instance, grid following resources on the left, where you're not controlling the terminal voltage as well, you have that larger impedance, you see that the PV curve falls off a lot sooner. Whereas for a good voltage regulating resource like a grid forming inverter, that impedance is smaller, the PV curve remains closer to the idealized curve for longer. And so beyond the idealized curve, you certainly are unstable. Within the bounds of the curve of this dynamic, where the dynamic impedance is applied, you have stable operation. And somewhere in between, you have some marginal stability where, frankly, this method just doesn't have that fine of a point, right? But what you can see is that there is a substantial difference reflected in how much power you're able to transfer across the system with how your resource is behaving and how well it is controlling its terminal voltages. And these differences can be quite substantial. And so the assumption that you're making in terms of those resources has that big effect on power transfer and the stability of power transfer. So great. What do we do with that? How does this work with the tools that we know today that we're comfortable with using, that the staff and the teams are familiar with using and doing? How do we integrate this into our processes? Well, taking, for example, you have a contingency analysis. It's a steady state analysis. It draws on inputs, the topology, these models are built, the contingency lists are built, and you're tweaking the scenarios, the resource mixes that you might expect to see in 10, 20 years out, right? And you're doing a contingency analysis and you're getting a bunch of results. And what we're proposing here is that this process could be augmented as what's on the bottom and what was highlighted in kind of an orange color, where you are now augmenting that analysis with the extracted important characteristics of different resources based on the detailed PS-CAD models. You're applying this method and the output of that being the dynamic impedance, which you can then integrate into your steady state stability analysis. The output of that is a pile of results, and you can run this in large systems, and you can look at a lot of scenarios in a reasonable period of time. And it allows you to identify those critical conditions, those locations of those resources, the qualities of those resources, the disturbance, the limiting phenomena, et cetera, and help you get down and identify the subset of cases that you really care about, where then it makes sense to use the other tools, the positive sequence simulations and the electromagnetic transient simulations, in a more strategic and thoughtful way. And so really what this allows here is that it's a new knob for planning, in a sense that in a steady state stability analysis environment, you're not just looking at your resources as a monolith, as idealized voltage sources. You can now differentiate them, and you can understand, okay, if we have a heavy grid following region, or a heavy grid forming region, or still some conventional or something else, what does that do for the system? And what does that allow you? What does that enable you to do in terms of power transfers? Where are the weak spots and where are you limited? And then go after those spots. So in that, there's a mouthful, but thank you very much. I'll hand it back over to Jason.
So now I'd like to take the next step in our journey with Jin Tan. Dr. Tan is principal engineer and a distinguished member of the research staff and in the Power System Engineering Center at NREL. She joined NREL in 2015 and leads the development of a multi-timescale integrated dynamic and scheduling model called MIDAS to address the challenges of planning and operation in extremely high renewable penetrated grid. She's also working on developing advanced electromagnetic transient simulation capability in the power grid and a large amount of distributed energy resources supporting 100% renewables. She received a presidential award from the National Renewable Energy Lab in 2018 and 2020, and IEEE Best Paper Award in 16, 18, 19, and 20. Please help me warmly welcome Dr. Tan.
Right. Good morning, everyone. I'm Jin Tan. I'm from National Renewable Energy Laboratory. And today I will talk about our analysis of these 19.5 Hertz oscillations on Kauai Island system. First, I would like to appreciate the ESIG conference, because I think this is very magic. It magically brings all our partners and team members in this meeting. So Andy Hook is there, and the Cameron from the KIUC, Kelsey from the AES, and also a lot of friends from the HICO. So I swear they don't come for this presentation because we already discussed it 1,000 times. All right. So today I would like to share what we have learned, what we have done so far for this event analysis. I have to say there are still a lot of open questions under this investigation, but we would like to share what we have done so far and to seek the inputs. So first, I will work through with you. So first, what happened on this island system, and what we have done, and what's the oscillation source, and also what's the root cause of this oscillation. Eventually, how do we propose the mitigation methods for this event? First, let's talk about what happened on this system. So one day, actually, we had a project meeting with Cameron, who was sitting there yesterday, and he told us, hey, you guys, you should look into this. This is important. And then we know on November 21st, 2021, at 5 a.m., and actually the largest generation on this island is called the KPS, is tripped. At that time, it was supplying 60% of the loads. And meanwhile, they still have a small amount of the hydro biomass and the 4 battery energy storage online. So when we heard about this, we think this is a very unique opportunity for us to investigate this event, because it's night, so no PV online. It reduced the complexity of this analysis. So after this event happened, actually 4 battery energy storage, including 3 fast response for grid following inverter and 1 grid forming inverter in terms of the VSM. Actually, they are responding super fast. So here I just want to let you understand what they are, because later I will use it a lot. So this is IBR 1, 2, 3, 4, and IBR 4 is the grid forming inverter. So they are responding super fast. Actually, this avoid the significant load shadings and the possible blackout. But still, we see very significant 19.5 hertz oscillations. It lasts for over 1 minute. And this is actually a framework we used for this study, but actually we didn't put it up at the very beginning. We kind of like have this framework after we finish the investigation. So the first thing we have done is we need to talk to the partners. We need to understand what happened there. We need to align the events and the control actions with those frequency data, with the power data. And the second thing is we know this is a rare opportunity for us to collect the real data, trying to do the analysis. So we collected the low speed data, high speed data from the KIUC and to do this analysis. Then we need to understand, okay, who bring the trouble to us? Who caused the oscillation? But only understand who is causing the oscillation is not enough, because we want to know why this happened, where it happened in the future again. That's why we continue to develop this EMT model, try to replay the events. And even with the time domain simulation, sometimes it's still lack of the insights. So we developed a small signal model and try to understand the root cause related to those IBR related oscillations. Based on all of those models, measurement data, we start to propose the mitigation methods. So this is kind of like a process we have done, and I will walk through you with that one step by one step. So first, oscillation source identification. As I mentioned at the beginning, actually this is the most straightforward way how we should do it. Actually, KIUC and AES took a really quick action on that and doing a fantastic analysis, because the real data tell you a lot of things. They pull the data from the digital fault recorder and they try to understand, okay, how the frequency looks like, how the power response looks like from all the IBRs. And they start to analyze the data, and we found that we could see the significant oscillations, and also can see the IBR 1 is and 2 are oscillating against the IBR 3 and IBR 4. But after that, what should we do next? We should do more to understand the data. But at that point, we realized that we need to go back and revisit the data. First, data is telling the truth, but sometimes they are dirty. They could be missing, and you need to do some process there. So we start to do another round of the analysis by using this probability analysis. The reason for that, actually, you probably can see after we matching the power data with the actual units power, so we can clearly see 2 things here. So one thing is, we could see who is oscillating with who. The purple one actually is the grid forming inverter is IBR 4, and the green one is the IBR 3. Actually, they are oscillating against the IBR 1, IBR 2, as you can see here. But the IBR 1, IBR 2 has the largest magnitude. And meanwhile, we also can see after the event happened, IBR 4 actually responds very fast. It's the grid forming, so it has the sort of kind of the inertial response here. And also through this probability analysis, it can give us the mode shape. So we also can clearly see who is contributing to this oscillation mode, and also who is oscillating with who. After we did that, we kind of like get a sense, but still we know traditionally there are a lot of oscillation source identification methods, but none of them has been proved. It had been proved for the IBR dominated grid. That's why when we selected the oscillation identification source identification methods, we still keep a question in mind. So are they accurate enough? So while we are using actually we pick up 2 methods. to do the identification. One is called this dissipating energy analysis method. Another is called this super synchronous power flow analysis. So it's super easy to read this figure. So if the energy is larger than 0, which means it's the oscillation source. If for this figure, if the PSC matrix is below 0, which means it's contributing to the oscillations. So basically those two methods give us the consistent answer. IBR1, IBR2 definitely is contributing to these oscillations. And also IBR3 and 4, if you zoom in, actually IBR4 is providing some sort of the damping here. So this can like give us increase the confidence to trust those oscillation source informations. By now, we already understand, okay, IBR1 and 2 may be suspicious, but what caused this oscillation is still unknown. That's why we start to develop these EMT models with two purposes. One, we need to recreate these 19 Hertz oscillations so we know what happened there. Second, we want to propose and test the mitigation methods and by using this model. The key takeaway message from this development is we realize that the model accuracy of the IBR model is super important. And also this is also our challenge. Before we receive the vendor provided model, we use the generic grade forming model, grade following model, to try to replace this 90 Hertz oscillations. We do very comprehensive steady state validations by using the SCADA data. And as you can see here, no matter how we try to retune in the controls, actually the right line is the simulation data. So no 19 Hertz oscillations. And next thing is, the good news is eventually we receive the vendor provided model and we start this, we start to connect it to our grid. We hope the magic happen. Actually, no, still no 19 Hertz oscillations. Then we realize that actually vendor provided model don't reflect the dynamic performance of the IBR in the field. So we test it through this single infinite bus. We retune the control parameters of the vendor provided model by replaying the DFR data at the point of the POI. And so I think this is a significant, important step. Need to make sure actually the model can actually reflect your field and the dynamic characteristics of your field devices. So this is before the parameter tuning, and this is after parameter tuning. And the blue line is the recorded data, the right line is the simulation data. So after we complete all these tunings one by one for each IBR, for all the battery energy storages, then we connect it back to the grid again. Boom. Yeah, this is what we got. So we got a full EMT model to represent the entire KUC system for that point. And we could replay this 19.5 Hertz oscillations. And we got pretty excited to get these results after we can replay the event. But still questions remained. This is another validation through the mode shape analysis. Just want to show actually they match pretty well. But still the question remained. So for the time domain simulation, we could replay it. Now we need to understand what caused the problem. Actually, there are two ways to do that. One way is to develop this EMT-oriented small signal analysis model. Our partner, Purdue University, actually helped us to develop this modularized small signal model for the KIUC system. And a long story short, so by developing this small signal model, actually we can use in the eigenvalue analysis, trying to help us to understand two things. First, who is contributing to this 10 to 20 Hertz oscillations? Actually, we can easily find out that, okay, these three grid following inverters actually introduce these modes. They are potentially to be the oscillation source for this, to be responsible for this oscillation. And the second thing, if we analyze the participation factors, we also can pinpoint to actually the PIL and also the current control loop actually play an important role for those oscillatory modes. And we conduct a sensitivity study by changing the control parameters we have identified as the critical here. And we tried one by one because this is much faster than the EMT simulation. So it could clearly see actually the eigenvalue trace here while it's moving from the left to right, which means it becomes less damped. So we compare those things, for example, before event, after event, we definitely see those oscillatory mode becomes less damped. And then we tune the control parameters and we found that, okay, definitely tuning the droop parameters and as well as the PLs could be the most efficient way to damp these oscillations. After we identify that, we need to validate it because small signal model is based on the linearized model. We don't know how effective it is. So we go back to our EMT model and we try the first mitigation method, which is adjust the PF droop. And we tested it. We changed both PF droop constant from 3% to 4%. And after we change it, the blue line shows after we do the control parameter adjustment. And it could see that it mitigate this method and remove the peak if we analyze it from the FFT analysis. This is the one thing we have done. And another thing is about the PL parameters. We also did some EMT validations and just reduce the proportional gain of this PL. And it also can help to mitigate this method. And in parallel, actually, NREL team also doing very extensive EMT study, trying to identify the source, identify what's the critical parameters. And additional information we got there is actually we tuning 40 parameters of this model one by one, and from the synchronous generator even to all the IBRs, and we identify that this oscillation is related to the active control of the active power control of the IBRs. And we also identify that those related to doing the sensitivity study and find those critical parameters. So compare with those two methods to find out the mitigation method. I think both of them are work, but it depends on how much time you have and how much effort you need to develop that. So this is the method 2. And then the third one, actually, everybody know that a lot of people are talking about this grid forming definitely can increase the damping of the system. So why not try the grid forming? The first partner tried actually is KIUC. They just move forward with converting one of the IBR1 HPP plants to the grid forming inverter. And this is the result is showing actually last year on September 15, similar event happened again, but with a smaller amount of output from the KPS. As you can see here, after we converted the IBR1 into the grid forming mode, this definitely can smooth the entire event. But we are not still fully persuaded because this is a smaller generation trip event. So we go back to our EMT simulation and we also validate these thoughts. Basically, which means if we convert one of the IBR1 or IBR2 into the grid forming inverter, it can help to mitigate that November 21, 19.5 hertz oscillations. So, okay, that's pretty much what we have done there. So what's the key lessons we have learned from this investigation and from this entire analysis? So first thing we have learned is actually the real world data, the field data is really important. It tells a lot of information, valuable information during this study. And meanwhile, we also need to be cautious when we are trying to use those information because it could be, data could be dirty. And we need to understand what the data we need to use. the lessons we learn is we need to do the cross validation through those data. And the reason for that, sometimes your device, your app tell you, okay, this is something you need to, this is the power, this is the frequency. Actually, if you use the point on wave data, you probably will feel this data is probably not that accurate. So which one you need to trust? This is why we learned while we are trying to do this type of study, we are trying to have the cross validations through all the data. Second thing we have learned is the model accuracy is very important. We have spent a lot of time to tuning the model to replay this event. That's why this makes us think about in the future, maybe we should consider either a way to do the model validation after the event happened. So should we develop sort of a protocol or some procedure and to facilitate that? I think that's important too. The third thing we have learned from this investigation is understand those root causes are also important for us. Trying to, if we want to kind of mitigate those risks for the future, we need to understand what's the real root cause for those similar type of the oscillation event. As you probably see, there are increasing 20 Hz oscillations in this field, in the world, all over the world, but they may have the different root causes. So how do we better mitigate those risks is something actually, as the researchers, we are willing to do here. So then that concludes my presentation today, and thank you.
From Dr. Ulrich Münz, and he's going to be talking about dynamic performance optimization there. So Dr. Münz is a principal key expert for generation automation technologies of energy and manufacturing systems at Siemens Technology in Princeton, New Jersey. He's leading multiple U.S. Department of Energy funded co-innovation projects for high renewable penetration utilities like Hawaiian Electric and research partners like EPRI, NREL, and PNNL. Ulrich received his 2021 Edison Patent Award of the R&D Council in New Jersey and is also a Siemens Inventor of the Year in 2021. So please help me welcome Dr. Münz.
Thank you very much. Thank you very much, Jason. And also thank you very much for Charlie and the organizers to organize this workshop and this nice session, and especially for organizing the presentations within the session, because as you will see, my key takeaways from my presentation will be very similar to what Jin just said. So it's actually a perfect back-to-back match of these two presentations. I will talk about dynamic performance optimization for 100% inverter-based power systems and the experiences that we had from a project together with our colleagues from Hawaiian Electric and other partners. A lot of discussion has been here over yesterday and today about planning and integrating grid-forming inverters. I want to take this into a little bit different perspective and take you on a short time travel. Let's look maybe 10, 15 years into the future. Imagine you're a system operator, you're operating a larger islanded or maybe not islanded transmission system. There's a lot of renewable integration in your system. Maybe there are days when you have 100% wind and solar generation, but of course there are also other days where you have much more synchronous generation. And there are many challenges, and of course all of you are aware of many of these challenges, maybe not all of them in detail. So I'm just really going through this really quickly. Power balancing, making sure generation meets load. Yesterday we had a presentation about hydropower, pumped hydropower storage. Of course, electrical storage is a big topic here. Energy market was a big topic last year for ESIG. Another big topic is power transfer. Generation will not be close to the loads, at least not all of the time. So we need non-bio alternatives, HVDC, and again, there's a bunch of things that we need around this. Another topic, which again also is very relevant here and which you saw it in the previous presentation, is power system stability. And that's the topic of the presentation I will give you today. I will talk about N-1 security. And if time permits, I will give you a quick sneak preview into a new project we just started a few months ago, again with Hawaii, looking into protection for inverter-dominated systems. Obviously, there are no results yet. We just started a few months ago, but maybe then there will be results in the future. And I think it's a very interesting and complementary topic. Now, as we talk about N-1 stability, I could probably almost skip this slide just looking at the previous presentation, but I still want to give you an impact. Is this just a 90 Hertz oscillation phenomenon on some small islanded system, or is it a bigger problem? So I brought you two figures. Left-hand side is from island, right is from Maui. This is actually already more than 3 years old. You see here at the bottom left, the red curve, which is the demand for island, and the bottom is the blue greenish curve is the wind generation. This is for 1 day in February, and you can see that during the night, the wind generation is obviously curtailed in order to ensure there's a certain number of synchronous generators running 24/7 off the island. We've seen yesterday presentations from National Grid, Australia, ERCOT. It's kind of the same story for all those systems. One reason, not the only one, a big reason for this is, of course, to maintain system stability. We cannot run systems today, at least not at this size, with 100% inverter-based generations. And of course, this is not just a one-day event. If you look here at the whole February, what I find really astonishing is that you see the dips in the blue curves every night, almost every night. So 20 out of 28 days in that month is already curtailment is taking place just in order to ensure system stability. The right-hand side is a different graph, but kind of the same message from Maui. This is the renewable generation from different quarters. It's probably difficult to read, but this is one bar basically for each quarter from 2020 to 2022. And the blue line here at the bottom shows what is the renewable curtailment. So it's on average about 10%. And again, it's a similar message that I got from HECO, is that a lot of this curtailment is done in order to ensure the system is stable. And we need to ensure system stability, so we have to curtail renewables. So the question is, what can we do in order to overcome this curtailment, reduce this curtailment, and eventually get to 100% inverter-based generation? This shows you from, again, connecting to sessions we had yesterday, how do we ensure actually N-1 security in operation? Again, I'm not talking about planning out, talking in an operational setting, thinking of, again, 10 years in the future, operators sitting in an operation room. What are the tools that they need? That was actually the starting point with our discussion with HECO when we started this project. Obviously, has been discussed here quite a bit. We need grid forming inverters. Maybe not all of them. There's been a lot of discussion yesterday about specification. It's a key component for them. We have to interconnect them. And again, there was a lot of discussion also already about going from RMS into EMT. Do we need EMT? Maybe in some cases, or we should be very specific when we actually need them. So there is a lot of work, I would say, right now going on in these two fields here in the bottom. Now going one level up and thinking about larger interconnected systems. What you expect, of course, is there are different generation mixes changing from hour to hour, from day to day, from week to week. You may have times when you have inverter-only systems. There are times when their systems are dominated by synchronous generators, and then there are mixes in between those. And the larger your system, the more generation units you have, the more of these different changes you had. And what this leads to is that you have time-varying eigenmodes of the system. We saw it in Jean's presentation. Before the outage of the generator, the system was stable. There was no 90 Hertz oscillations. And then actually the poles moved to the imaginary axis after one generator was taken out. That was one extreme case. But if you think of a large interconnected system, you expect this to happen just as you normally start redispatching dispatching your generation units. And of course, we have to make the operators prepare for these time-varying oscillation modes. The continental European system and all larger interconnected systems have a fixed number of generation modes. There's a lot of planning studies, of course, going on in order to tune parameters of the different generators to damp those oscillation modes. But if the damped oscillation modes are changing over time, it's very difficult to find one set of parameter which would damp all these oscillation modes. So we have to get into a mode, and this is here the point on the top. We have to adaptively damp the eigenmodes of the system depending on your generation dispatch. Now, what we did with Hawaii is to develop a demonstrator that shows how something like this could be done in an operational setting. So we took the original needs from Hawaii, maximize renewables, ensure resilience, operation closer to the limits, so all these kind of things that have been discussed here, and we built a demonstrator. And I will quickly take you through this demonstrator, and then I have a video where I show you how this demonstrator is working. We did not do it on the real island, as you can imagine. We are not there yet, but we converted a PSSE model from the planning team of HECO into an EMT model that is running in real time in an Opal RT system. Opal RT is one of our collaborators on this project. And then we built a demonstrator which contains like a hardware in the loop test bed, where you have a simulation of the Hawaii, and then you have an energy management system, commercial energy management system sitting on top of this. In this case, it's Siemens, but it could be another vendor, just executing a state estimation. And then on top of this, what you see here, we build an operator support system, again, building on partially products from Siemens, but partially also new tools that ensure N-1 security of that system. So it consists of first an analysis of critical contingencies. Unfortunately, it's a little bit difficult to see here, but you see oscillations similar to the ones that you saw in Jin's presentations. This is obviously simulation not from the field. Yeah? And if these oscillations are too heavy or too dominant, and you see the system is insecure in the operator, you want to have a suggestion, how can I improve the N-1 security for my system? So we developed an optimization tool that actually dampens these oscillations. And even this is actually very similar to what Jin showed. We have these oscillations, we go in the frequency domain, the peaks in the frequency domain correspond to the oscillations in the system. So we developed an algorithm which suppresses the peaks in the frequency domain by tuning the different controller parameters that you have in your system. Jing was talking about droop gains. This is an example. If you have conventional power plants, it could be parameters of your power system stabilizers. It could be practically any parameter that is tunable during operation of any of your generation assets, right? I mean, there's a separate discussion. Where do you have access? Do you own those assets? It's a separate discussion. But technically, we could tune all those parameters. And then obviously at the event, we do an evaluation for the operator sees, okay, this is the improvement, and then we can send it down to the system. This loop is running maybe every 15 minutes, whenever there's a major change in your system, a generation dispatch, and so on, right? Or you could connect it even to the market and say, when the market comes up with a new result, you're validating this in this fashion. Once the parameters are in place, you do this all before any contingency happens. So when a contingency happens, the system is supposed to be resilient against this contingency. So you don't need any real-time communication. You're relying on existing control loops, which are already in place. You don't need any wide area control or anything like. So in order to show you how this demonstrator looks, as I said, I brought a little video. I will just jump through a few parts of it. So this is again the loop that we did. I will start with showing you the use interface developed by Opal RT. So you see here a single line diagram. Here you have active power, reactive power, voltage, and frequency from the generation units. We modified the system just a little bit in order to get to these 100% scenarios. And then from this real-time simulation, we feed RTU data into the Spectrum Power 7 energy management system, which is then receiving the data and then running a state estimator in order to get a snapshot of the system. This is all standard functionality. This is something that you will find in similar SCADA products from other vendors, of course, as well. And then we take it into this operator support system. Again, part of this is a already today available commercial product. Part of it is a new development within this project. Sorry, no, that was not the intention. Just giving you a quick heads up. So this is the cockpit for SIGA dynamic security assessment. You see here a bar which kind of indicates green means your system is very stable. Red means that there is quite some challenges. This is the original parameterization of the system, which shows that there is a high risk of maybe a blackout, or at least a behavior that you can determine KPIs that measure how secure is your system. Let me see if I can stop this. Somehow I cannot. To take this here. Yeah, and then we see, sorry for that. We see here that the optimization is then running. Again, everything is running closed loop in real time while the power system is still operating. And at the end, you see here the optimized parameters show you a significant improvement in the resilience of your system. And of course, you can look at simulations. There was a question before about EMT RMS. Those simulations are running RMS because they have to run in real time. And technically, it could be EMT, but at least today, I think it's too slow for that. And then we validate this again in the real-time simulation. So you can here execute different contingencies. I have a separate slide to show you which contingencies. What we are executing here is the outage of one of the grid-forming battery units. And you see here the transients. And what's also quite nice is we can run the same contingency twice, once with the original parameter set and then once with the optimized parameter set. And what you can see here at the bottom is a comparison of the system behavior with the original parameter set and the optimized one. So similar again, what Jin showed in the planning studies. This is not a very extreme case, but let me go to the next slide to show you the results. So we looked at different load and generation scenarios. They are actually very close to what HECO is doing today in planning studies. There is a noon case, an evening peak case, and a night case. We have different generation mixes, SNSP, synchronous, non-synchronous penetration system, non-synchronous penetration. 100% means it's inverter only. 90% is there's one large generation unit, and 80% means there are two large synchronous generation units. And then you see here at the bottom the different contingencies we analyzed: loss of a largest synchronous unit, loss of a power line, loss of a grid forming unit, loss of a grid following central unit, and also a big issue we heard yesterday from Cameron about Kauai is loss of 50% of distributed PV. That's a specific case in Hawaii. And you see here some of the examples. The left-hand side is always before optimization and after optimization. And even though it's difficult to see, you can see some cases like up here and this one where you have persistent oscillations actually with before tuning. And then with the tuning, we get system behavior, which looks much nicer, right? And again, closing to loop what Jin said, tuning controller parameters helps you in order to get into more stable system behavior. Now, let me close with lessons learned. And again, this is very close to what Jin said earlier. One key message is that I expect we will have time varying eigenmodes in the system, and we have to deal with it. So we need support systems for the operators. Of course, we have to deal it during planning, but also the operators need help and the right tools in order to do the assessment and the adaptation of controller parameters in order to adjust N-1 security. Do we need an online optimization? Honestly, I think this is not the first step. This is something we did here because we wanted to make a big jump ahead in this US Department of Energy funded project. Probably you would do first an offline specification of what are the good parameters of the system. And then online, you just switch between different parameter sets, maybe for different generation mixes. I think for Hawaii, since it's a relatively small island, it will be relatively easy. When you talk about larger systems, National Grid, Australia, Ireland, Texas, it may be more difficult and or more diverse set of parameters. Second big topic, and again, I'm just supporting what Jin said earlier, accurate models. We need accurate models of the power systems. They did a great job for Kauai to actually fit the model to the measurements. We've tried something similar with Hawaii. It was not the main focus of our project, so it was not something that got to the point that I would say this is a done deal. There's definitely a big gap still in calibrating dynamic models, either RMS or EMT, in order to ensure, of course, also that this kind of parameter tuning is effective. And last but not least, also something that was discussed already the last few days is inverter models. So we need accurate inverter models, especially for grid forming. The specification we were discussed yesterday is just one piece of it. It's basically what we as or you as utilities require the inverters to do. But if you want to do simulation studies, if you want to do any kind of parameter tuning, you need models, ideally white box models that you can use. What I envision is that there will be an IEEE standard at some point in the future, similar to what we have today for power system stabilizers. There's a set of 10, 15, whatever models for grid forming, and then each vendor can pick and say, this is my model, this is my parameterization, and within certain parameter ranges, you can change parameters and the model behaves like this one. This is last part about this project. I just want to give a quick outlook into a new project that just started a few months ago. Now we're looking again with HECO into the second open problem I mentioned earlier, protection. How do we protect a system like Hawaii, Kauai, and similar ones if we go into inverter-dominated systems? It's a big topic. I'm happy to chat with you over a coffee break. We're working again with HECO, EPRI, Sandia National Lab, Manitoba Hydro, and Electronics on this project. And we were looking both into the inverters and into the protection functions. We are developing a co-simulation between PS Escape and PSCAT to actually have analysis for this kind of issues. And of course, looking then again into hardware and protection hardware in the loop testbeds. Thank you very much.
Excellent. Thank you, Dr. Münz. I think we're going to wait until the end for the remaining questions. We still have two speakers that we'd like to fit in. And next, I'd like to transition to Dr. Yue Zhu. And he received his Bachelor's of Engineering and Master's of Engineering degrees in Electrical Engineering from Zhejiang University in China and his PhD degree from Imperial College in London. He is now a postdoctoral research associate at Imperial College, supported by National Grid Electric System Operator. And his research focuses on impedance-based stability analysis of power systems, data-led stability modeling, and analysis of grid strength for inverter connection assessment. Please help me welcome Dr. Zhu.
Thank you, Jason, and thank you, everyone. So my name is Yue Zhu. I'm from Imperial College London. I'm a research associate there, and I work with Professor Tim Gray. So I also appreciate ESIG to give me this opportunity as well. Thank you, ESIG. Today, I'm going to introduce our recent progress and some explorations on the project about new system strength metrics. This is also a project funded by National Grid ESO. Thank you, National Grid. So I'm just going to do a quick background introduction. We know the power system is transforming from a synchronous generator dominated system to a system where inverter-based resources, IBRs, are coexisted. And conventionally, the system is basically a physical defined behavior, but right now, because the behavior of the IBRs are mainly shaped by their control design, so it becomes a control defined behavior. So that such change has brought us lots of flexibilities, but meanwhile, it gives us lots of instabilities. Several famous cases in the UK is in 2019 in August, when there is a lightning strike happening in the UK and caused oscillations in the offshore wind farm, and therefore caused a serious effect and caused a nationwide power outage. And 2 years ago in Scotland, there is a double heart attack, so-called double heart attack, with 8 Hz oscillation founded, and it appears they were introduced by the progressively increasing of renewable output, and some users were tripped off during the disturbance. And here in the US, just as Dr. Tan just introduced, the 19.5 Hz of oscillations have introduced as well. And so there are lots of things happening here. So many instabilities has forced us to be careful every time we are going to connect new IBRs in the system. And to assess that, we need to assess the grid strengths. The first question is about what is a grid strength. So basically, we will use short circuit ratio to describe the grid strength, but grid strength is not short circuit ratio. Short circuit ratio is not grid strength. So basically, the strength of the grid is about its connectivity. Is that when we are going to connect a new device, say bus K here, and we need to stand at bus K and see the grid and say compare the power and see if it will be safe for us to connect this new device to this bus. And then we'll need the assessment of the grid strength. So to do that, we'll usually do a Thevenin impedance of the network seen from bus K, which will be a voltage source in series of Thevenin impedance. And when we are considering a short circuit happening at that bus, we will have the short circuit capacity, which is a power flowing from network to that bus when it is short circuit. And short circuit ratio is then defined as a ratio between the short circuit capacity between the nominal power of the device that we are going to connect. So it's actually a relative value that we are going to assess. It's not an absolute value. And based on some experience from engineers, when short circuit ratio is larger than 5, the system can be treated as strong. When it's larger than 3, smaller than 5, it is weak. And when it is between 1 and 3, it's considered as very weak. And when it is equal to 1, it actually reaches the boundary of stability. There are some other understandings of short circuit ratio from different perspectives. If you understand that you are connecting a voltage source in the system and it is trying to deliver its nominal power to the system, then we know that when the power angle reaches to minus 90 degrees, the system reaches to the maximum absorber power. So the short circuit ratio is therefore actually the maximum absorber power of the grid to the nominal power of the grid. It's a ratio between the power margin of the, and if you understand from impedance perspective, and if we consider a current source a load at nominal power and trying to maintain the voltage bus, and then we know that if they are exporting their nominal power, they can be equivalent as an impedance with value of 1 over their nominal power. And then from some circuit principle, Ohm's law, we will know that when that impedance is smaller than the 7-9 impedance, the voltage at the terminal will collapse. So that means the 7-9 impedance is actually the minimum allowed impedance that you can connect to that bus. So short circuit ratio is also an impedance margin ratio based from this perspective. And after we understand it, let's see what happened if we have more IBRs in the system. The IBRs have some different characteristics, especially some small signal oscillations happen. And when we are connecting a group of wind farm, interactions are found between each of the wind power plants in this group, and also between the group of power plants to the main network. And convention, also we have grid forming inverter, which are grid voltage sources, and grid following inverter, which are usually treated as current sources, but they are all treated as voltage sources in the conventional short circuit ratio. The control-defined behavior and the IBR tight constraints has caused a reduction of system strength, and there are several emerging problems that is unique to the system with IBR penetration. We have inadequate voltage regulation, we have increased recovery time from voltage dips, potential instabilities of grid following inverters, and more operational protection. And SCR, in such case, is no longer a good all-purpose indicator, and we need to define something new. And to clarify, and our idea is actually to get a set of new grid strength metrics to address to each of the problem individually. And we have generally separated the grid strength into a small signal strength and a large signal strength. For small signal strength, it is mainly focusing on the small perturbations around operation point. It is analyzed in frequency domain, and it is analyzed in small signal scope. It aims to solve some potential instability caused by inverters and small signal interactions among inverters, such as those oscillations. There are some existing studies proposed by University of Strathclyde called GSIM, and small signal generalized short circuit ratio GSCR proposed by Jordan University as well. And we are going to propose something different, but more accurately called impedance margin ratio, IMR. And for large signal strength, it aims to focus on the system strength toward large perturbations, and it is analyzed at fundamental frequency, and which would be a further extension of the traditional SCR, but considering more. It considers interactions among IBRs, the increased recovery time from voltage dips, some low fault current conditions, and inadequate voltage regulations, and more operational protection. There are already several existing methods in this area. I'm going to introduce them briefly later, and we are trying to propose something called type-dependent short circuit ratio. For small signal strengths, in our previous study, we have tried to use the impedance model to represent the dynamics of the entire network, and we call it a whole system impedance model or a whole system admittance model. If we are introducing a small signal voltage perturbations at each of the bus, and we take the current response at output, and then from the input to the output, we can have a transfer function matrix, and we call that the whole system admittance model of the entire network. It contains all the dynamics of the devices and of the system as well. If you pick out one of the diagonal elements of that matrix, you can just find that the equivalent circuit is essentially the same as how we define the traditional SCR. If we are considering a small perturbations happening on the nominal power, it will essentially lead to a small change on the local impedance of that apparatus. And that local impedance will therefore cause a change, delta lambda, on the system eigenvalue. We have proved that if you use the residues of the whole system admittance term, you will be able to calculate how much delta lambda will be. And to maintain small signal stability, we always keep in mind that we need to keep all the eigenvalues in the left half plane. So their real part must be negative. Considering that condition, we can further get that the maximum variation of the impedance you can have, and then which it will give you the ratio between the nominal impedance and the minimum impedance you can have. And we call that the impedance margin ratio. It is equivalent as a meaning to traditional short circuit ratio, but the evaluation is carried at S equal to lambda, and lambda is the oscillation mode of the system. So if you see from this picture, and the blue arrow actually refers to the original impedance of the apparatus we are going to connect. And the small circle on the right top corner is the margin of the variation that it can be. And inside the mode is the instability area. So the IMR is essentially referring to the ratio between those margins. And so we know that it must be larger than 1 to maintain the system stability. And when it's larger, it means the mode is less sensitive to the connected apparatus. And it is also to be noted that IMR is based on small signal analysis, hence it's only valid around a small range in an operation point. And if you want to do it over a larger range, and you need to do it in an iterative way. So how to use IMR in practical? So first case, that considering if you are going to connect a new IBR in the system. And at that point, you can extract the information of the network impedance spectrum, which is actually the Thevenin impedance spectrum. And then if you have the apparatus spectrum as well, you can just combine them together to get the whole system admittance model, from which you will be able to extract information of the oscillatory modes as well as IMR. And this information will further tell you, will new bad modes be created after the connection of these new apparatus? And also, this actually refers to the interactions with other IBRs. And it also, if you found that there are small IBRs there, or IMR there, it means the strength at this point of interconnection is low, is weak, and you need to be careful when you connect that. There are some other applications. You can also use IMR in a global wide, which is to identify the weak points of the network. If you do the assessment at all the buses in the network, you'll generally be able to find the potential oscillation modes in the system. And if you compare IMR at that oscillation frequency, it will help you to identify which bus is most weak towards that oscillation. And this is helpful to identify the risks in the system. To validate the online real-time monitoring, we have built a power hardware in the loop system in our lab, and we have used OPRT power amplifier, and we built a network in real-time simulator to simulate in real time, but we use a power amplifier to get the voltage information and generate exact physical voltage and connect that voltage to a real physical 10 kVA inverter. And in this system, we try to introduce the small signal voltage perturbations. We have done a frequency sweep, and generally we can get the whole system admittance spectrum. And NREL has done something very similar. They are doing it in a very large scale, a megawatt scale, but we are doing it in a smaller lab scale, but we are focusing on different stuff. And we have just got a paper published about this platform. And for large signal strengths, there are already some very fresh new concepts, and we are still exploring this area. So we just have some ideas coming out. So first, I'm just going to introduce some existing studies. We have composite short circuit ratio, which was proposed by NERC and JE in 2015. And we also have weighted short circuit ratio, which is proposed by ERCOT, proposed in the US, which is nice. Yeah. So it's these two metrics are mainly talking about when you are going to connect a group of wind farm to bus K, and you want to get an overall short circuit ratio to assess the strength at bus K. So in that case, you need to do some assumptions, like assuming all the wind farms, all the wind power farms in this group of wind farms are connected to the same MV, and therefore you can just do a combination of them, and which is actually the way we use in composite short circuit ratio. And for weighted short circuit ratio is you do a weighted average of all the buses and then just treated them identical and plus them together. And they are aggregated indications, incidents to represent the grid strengths. We also have equivalent short circuit ratio, which is proposed by our SIG report in 2016. And it is actually used in the same situation, but it focuses on individual SCR at different wind power plants. So it considers the interactions among the wind power plants in the same group of the wind farms. So it's that there is an interaction factor which can be derived from the transfer impedance between the two buses and over the impedance of the Thevenin impedance at that bus you are focusing at. There is also a set-dependent SCR, which is proposed by North Dakota University, and this is generally very similar as ESCR, but tries to extend it to a global area. And we are trying to explore a tap-dependent SCR. Because the previous method, they all treated all the sources as voltage sources, but current sources are not actually included. But we know that we have grid following inverters, and they should be treated as current sources when calculating the short circuit ratio. And to solve that, our idea is that you need to change the nodal admittance model of the nodal admittance matrix of the system into a hybrid matrix by picking out the current source in the system and swap their input and output. This transformation is generally simple and basic, but it can give you some information about whether you are going to connect a voltage source or a current source. And finally, the SCR is actually dependent on whether a voltage source or a current source is going to connect at that bus. Yeah, and for the low fault current, if you are considering the grid forming inverter are going to do a mode change during a fault due to its current limitation, you can just simply replace it as a current source and rewrite a hybrid matrix. If you are considering interactions among IBRs, you can borrow the idea of ESCR, but you have to be careful that there are 4 different situations of interactions in such case. And we have some further thinking about long-term strengths. SCR essentially is a short-term strength matrix because we usually consider the voltage as an ideal voltage source with a fixed angle. But the change of grid configuration can actually change the angle of that, and that change cannot be captured by the conventional short circuit ratio or by other short circuit ratio proposed before. So how might we define a long-term strength matrix? And we are thinking that we need to treat that voltage source as a voltage source according to time. It's a function of time. And from that, we aim to get a long-term strength metric to describe the system strength for a long time, for long term. That's it. Thank you very much.
Thank you, Dr. Zhu. For the interest of time, I think we'll round out for the last discussion. And we've heard a lot about analytics so far. We've heard a lot about capabilities of identifying where systems are at their pain points, at their pinch points. And then finally, from Dr. Zhu around the metrics that we're looking at differently. And the final presentation, I'd like to introduce Alex Shattuck from NERC, who is going to talk a little bit more about a collaborative effort in industry that's spearheaded by NERC around an EMT modeling guideline. So Alex is a senior engineer in the Engineering and Security Integration Department at the North American Electric Reliability Corporation. He contributes heavily on a number of NERC's efforts related to grid transformation, including initiatives focused on inverter-based resources, distributed energy resources, integrating security with conventional engineering practices, emerging technologies. Alex also has a plethora of energy industry experience through work at Vestas Wind and Siemens Electric Power Engineers, as well as New York ISO. So please help me warmly welcome Alex.
Thank you. Good morning. Thanks to ESIG for letting me speak today. It's always a little bit risky to give me a microphone, especially when I control the microphone. And second, I want to make sure that my colleague Ong gets his recognition for this effort. He really drove this thing pretty much the whole time and sacrificed a lot of sleep to get it over the finish line and get it approved at the RSCC last week. So this is actually a real approved guideline. It's out to read. We released the press report, I think yesterday or 2 days ago. and who is a little bit intimidated by all of the presentations we just saw. You know, we're very detailed, really in the weeds of EMT, a lot of hard work. And I can't believe I'm saying this, but I'm going to bring us out of the weeds for once. And we're going to do something, I'm going to present something that's a real different type of challenge, and that's getting all these smart people to actually agree on anything, and much less a document of this size to give the guidance to all of y'all who might be a little bit afraid of EMT and what's coming. This document hopefully should provide a lot of guidance for a number of EMT related processes and study advice. So this is a story of the EMT guideline. And every story starts with something unexpected happening, and the unexpected things we're talking about now are disturbance reports that NERC has published. These are events that happen on the grid that we have investigated, come up with conclusions. We posted reports. Most recently was the Odessa disturbance, published last December, and very similar to a previous Odessa disturbance. So that gave us a lot of motivation, as well as some other events, to kind of put together a guidance document, because what we were finding was we're not predicting these things. We should be predicting these things. We do grid planning, we do lots of detailed studies, but these things are happening, we weren't expecting them. So the Odessa disturbances, some other California disturbances, San Fernando, all of these things kind of contributed to motivations to write a SAR. So a document that basically says we need a standard or a reliability guideline or something to help the industry with these challenges. So who here has not done, raise your hand if you have not done any of these studies on the screen. Okay, very few. So these are all the study use cases for EMT. There's probably more, but they're very detailed models. They're relatively highly accurate, and we need to capture these things in order to make sure the grid is reliable. So there's a lot of them, I'm not going to read them, but what we've covered today are oscillations, control instability, power quality, trying to study high penetrations. It's all coming. We're going to have to handle it. We're going to have to tackle it together as industry. So we have a reliability guideline to help with that. So one of the big drivers, and this is a kind of a very scary slide. These are provided by ERCOT through their investigation of the Odessa disturbance, the second one. And the top left is, can the models that were provided, can they technically recreate what happened? So the first column is just all the types of tripping we identified. The second column is, can the RMS models recreate? A lot of them, yes. Some of them, no. Kind of 50-50 there. But if you look at the EMT, pretty much all of them are yes. So presumably, if the EMT models are accurate and representative, we would have determined these issues before they happened if the studies were being performed. So the second table is the scary table. And this table, basically everything's unknown. It's hard to read, but what this table shows is none of the positive sequence models provided were able to recreate the event, and none of the EMT models were able to create the event. Positive sequence is, what we always talk about is it's hard to make sure models are accurate throughout the whole interconnection process and commissioning. The EMT model column is a little bit more wishy-washy, right? They have models where they're being used. It's hard to use them. So were they being used? Were they accurate? That's where the unknowns come from. So why is this important? This is a slightly old graphic, but lots of IBRs are coming. So lots of new devices are coming to the grid. They all have very complex controls. And EMT modeling is going to help us figure out how they're going to operate together and on the system, and help us plan for these things before we end up with something larger, hopefully not, than any of the disturbances we've seen so far. So we need to kind of tackle these things before there's a bad thing that happens and we get forced to tackle them. So trying to be proactive here. So why EMT guidelines? They're kind of scary to a lot of people. Most of the industry gets a little bit nervous when EMT comes up. Just anything, so running the studies, getting resources in your organization to run the studies, having the necessary expertise to do them correctly, and to verify models and make sure they're accurate. Why is that important? EMT models can be used to capture previously unstudied performances. So, unbalanced grid faults, instability between inside your plant or other plants, IBR plants, different causes of tripping, DC bus tripping, instantaneous inverter tripping, unbalanced current protections. All these things are kind of living in the EMT domain. They're not going to get captured in an RMS model. So we also can use these since EMT models are typically vendor provided and site specific or product specific, we can kind of use these to fill in some gaps like models and matching facilities. A little bit higher fidelity will help us kind of put the pieces in place to make sure that these models can match facilities, and just to help with the inability to reproduce or to proactively show the trips and the outages that we've been studying through our disturbance reports. And this guideline can just provide a lot of references for TPs and PCs, transmission planners and planning coordinators, as they begin their journey towards spinning up the EMT resources and doing the studies and coordinating with your entities through the study process and your planning assessments and reliability assessments. The big takeaways from the EMT guideline are, this is intended to provide guidance for model quality checks, model verification processes. This will help industry close the modeling gaps or the knowledge gaps for EMT. It will also provide industry some guidance for what foundational knowledge is necessary to even begin these types of analysis, and to provide some background and knowledge for those entities to hopefully make some new modeling requirements and practices. So ensure that there's reasons for everyone to give good data and give good models. And we gave some guidance to make sure that EMT models are at least available. It's in italics, but make sure that at least they're provided, and they might not be needed for every study, but they should be provided and available to use and hopefully parameterized accurately. So that interconnection studies per FACT 2 and reliability planning assessments per TPL1 are as accurate as possible, right? The studies are only as good as the inputs. If the models are bad, the study is unfortunately not the best. In addition to all these things, we really focus on this guideline for model quality, model verification, performance issues that we see and how to mitigate them, addressing interconnection studies, how they should be performed, model validation checks for ensuring accurate data, and some guidance that will close all these gaps. Unfortunately, there are many gaps, but this will help kind of provide some guidance to close those things. So we're going to start with model quality, and I'm not going to go in the weeds, I promise, but model quality is complex, right? There's all these things that go into model quality. We use words like fidelity, which is basically are the bits in there, right? Are there other pieces of the model in there that can represent the performance of the product? Usability is very important. When people see EMT, they get kind of afraid. It's a black box model. I can't use it. It doesn't run. It runs slow. It's hard to set up. So usability is very important. If you can't use your model accurately, or you can't use it easily, it's a burden on TPs, planners, anyone using the model. So in addition to those things, we do validation, efficiency of the simulation. We rely quite a bit in the guideline on attestations from OEMs or the generator owners that say, this model was given to this plant for this product. The generator owner would say, this model is configured like I intended it to be designed, and then just accuracy of those things. So benchmarking, actual curve on curve validation, things like that. So don't read this. I'm not sure if you can read it. This slide is intended to essentially just show that when we say model verification is important, I don't want to say that it's very easy to do. So this is a very complex. There's a lot of invested groups. At the top, there's planners and coordinators. The middle is generator owners, and the bottom is OEM, the blue boxes. And all the arrows are basically things that they all do and coordinate with each other. So what this really shows is that it's a lot of moving parts. There's a lot of collaboration needed. There's a lot of detailed checks and iterations between them, and all of these things together should end up with an accurate model that represents your product or your plant or facility or whatever you're trying to build. So part of this is benchmarking EMT and positive sequence models. That the table from ERCOT essentially shows none of the positive sequence showed any of the behaviors, even the ones that were technically capable of being caught in the RMS domain. So what we want to make sure is that the assumption is that the EMT models are relatively accurate when compared to the product. If the EMT model is parameterized the right way, then you have a product representative EMT model. And then we want to recommend that that gets used as a benchmark for the RMS models. Because we talk about EMT, all the things that it can do, and that's all great. But at current, RMS models and studies aren't going away probably anytime soon. So we need to make sure that the RMS models are as accurate as they can be within the limitations of the software or the platform. So what we want to show is use the accurate model, benchmark it against your other models so that you have kind of a suite of models. So if ERCOT is planning and they do an RMS study and they do an EMT study or they do an operation study, that all of the models are matching so that the different groups aren't going to get different results. It's a way to ensure that everyone's kind of on the same playing field and all of those things match the product and the design. And this is just second bullet, it's kind of annoying, but we would recommend that benchmarking is performed for any modifications to the actual plant settings. You might be thinking that as you're interconnecting a facility, you're changing settings or performance settings or protection settings or things like that all the time. So how do you capture those things before studies? Checks back and forth between the entities and generator owners or OEMs to make sure that anything applicable, right, needs to get restudied. So applicable in this case is something that changes the performance of the plant. For other things, like maybe there's a new model version, it's kind of the advice would be to look at what that changes, right? The model version could be a change in the model for it's something in Germany, it's not getting used in the US. That's probably not an applicable update. You probably don't need to re-benchmark for your US facility. And it just generally mod verification is necessary to ensure study performance can actually be put into commissioning. So verification, the way we're using it now is slightly different than validation. Validation is taking the models, putting them on top of each other. Do they match? Verification is more like, is the same parameter in the product as the model? Are they the same units? Do they do the same thing in the code? Just because if you're doing all these detailed interconnection studies and there's a stability issue and you mitigate it with tuning, how do you get that into the field? You've got to have some sort of mapping or verification or attestation that the performance that you tuned for your planning study actually gets put into operation. Otherwise, you just are plugging unknowns into the grid until one of them is too unknown and something bad happens. This slide here is just, this is provided to us by an OEM for the EMT guideline. And this is just what we would say is a good example of EMT versus positive sequence benchmarking. The blue solid is PSCAT, the dotted red is PSC, and the dotted blue is TSAT. So this is one of ERCOT's low voltage ride-through profiles, part of the model quality test. And this basically just shows that for the specific OEM who spends a lot of time modeling and benchmarking, you can get a pretty good match, even for something with a voltage going down to 0 and a slow ramp back up. So this is one of ERCOT's kind of more severe tests. And you can see even during these conditions, these models were able to be benchmarked. And this is kind of what we would aim or suggest or kind of shoot for, is to have this type of match so that when you're doing these studies, you can be confident that everything is matching. We also focus on resourcing. We kind of hear it a lot in industry is, yes, we agree EMT modeling is important, but I don't have any staff. I don't have staff that do EMT. I have some staff who do EMT, but their expertise isn't at the level of some of these folks or some others who presented yesterday. And it's hard to get that experience because there's not too many resources out there for this, right? So in addition to the guideline and what's coming next, we also recommend that academic institutions, colleges, other professional training programs help with curricula for EMT modeling and studies. This will help kind of raise the industry floor for EMT modeling and concepts, and that's going to help us all move forward and use these studies to help us keep the grid reliable. And again, research institutions as well, national labs, more kind of educational things to get everyone on the same page. If you were wondering and you were worried that you missed the boat on the first EMT guideline, good news, there's a second part coming. And if you want to join that, you can go ahead and email me or Ong. and get on the listserv for that. And you can join in the meetings and arguments and discussions with us and get kind of involved and learn and provide guidance along as a second part to our first part, which is EMT modeling. The second part is more on studies, screening techniques, developing scopes for studies, processes, executions, all those types of things. And in addition to that, RSAC approved the guideline last week. They've also approved EMT task force, which is a task force that they stood up to, again, work together, provide guidance, develop technical documents. If you'd like to participate in that, Ong or me, just give us an email. We'll put you on the listserv. And just finally, want to make it clear that we're all in this together, which is kind of cliche now, but we're all working together to make sure that IBRs are reliable. There's a lot of groups in this little wheel, a lot of efforts, and we all got to work together or, the stool is falling down. If one of the legs is broken, the stool is going to fall down. So with that, thank you guys.